We now consider matrix A, and we will look at its rows and columns. We know that it has 3 rows and 4 columns. And we see that this matrix could be represented by these elements. You'll note that the first subscript is 1, and then the second subscript is a 1, representing row 1, column 1. This is row 1, column 2, row 1, column 3, row 1, column 4, makes up the whole first row. Okay, so all these little subscripts are pretty much like first name, last name, right? Row, column.
Most impressive.
So as we identify the following elements, we notice that A11 has a value of 1. A12, row 1, column 2, has a value of 0. A21 means row 2, column 1. So in row 2, column 1, we have a value of 0. A33 corresponds to this position right here in the third row, third column, which has a value of 1. And A34 is going to have a value of 8. As far as something like A43, A44, that would mean we're looking for something in the fourth row, third column. However, this matrix does not have a fourth row. So for example, something like A43, we would say that it does not exist. Does not exist. Okay? Never tell me that it's 0, because 0 actually is a value. The dimension of matrix A, well, the dimension is how many rows there are by how many columns there are. Okay? So we're going to label this as a 3 by 4. This is the dimension of this matrix A. If you ever consider some things in life that have different dimensions, for example, photos can be 4 by 6, 3 by 5. Lumber used for construction might be a 2 by 4. So you are aware of dimensions, and in this case we have row and then column with an X in between representing by. So this is read 3 by 4. For problem 4, we have win and loss table. It's asking that we express the results in a 2 by 3 matrix. Now if you look at this right now, in the way you see it, you would think that this is a 3 rows and 7 columns. But this is not how this works out. We want to go ahead and write this as a 2 by 3. It's asking for a 2 by 3, not a 3 by 2. So 2 by 3 looks like it's going to have 2 rows and 3 columns. Now if you think about the 2 rows and we look at this table right here, well, what would give us 2 options? You would note that there's a win and a loss. So your first row would represent wins and your second row would represent loss, which means that your 3 columns would represent each of the 3 people, Ed, Joe, and Lou. So now we ask ourselves, for Ed, how many wins did he have? 1, 2, 3, 4, 5. So Ed had 5 wins. What about Joe? Joe had 6 wins. Lou had 3 wins. And then we consider, well, what about losses? Ed had how many losses? Etc. So we've just created a matrix of the values, where in this case the win-loss was the row and then each individual was a column. So we have some different types of matrices here. In particular, we have 4 that we're going to focus on. A row matrix has only 1 row but any number of columns. A column matrix has only 1 column but any number of rows. A zero matrix is a matrix whose elements are all the number 0. A square matrix is a matrix that has the same number of rows and columns. Now, if it's not a square matrix, we tend to call them rectangular matrices. The transpose of a matrix, this is not a type of matrix, this is something or a property of a matrix, some kind of an operation that we may do on a matrix. The transpose of a matrix is when the rows and the columns are interchanged. Okay, so for any matrix A, its symbol would be A with a little power of t. So for example, if we have matrix A as being a square matrix with the elements 2, 1, 0, 8, then the transpose of matrix A would be 2, 1, 0, 8. Notice how this row became the column and this row became a column. So whereas in the first matrix A1, 2 was 1, right? Row 1, column 2 was a value of 1. When I look at the transpose, right, this blue one for example is A1, 2. That number became A2, 1. So the row and the column actually switched. Those positions actually switched. Okay. Here's another example. If I have matrix B is a row column with elements 2 and negative 3, the transpose, right, the transpose of B would be a column matrix. Note the dimensions here. This is pretty important stuff. So the dimension of matrix B is a 1 by 2, right? It's one row, 2 columns. When I do the transpose, it becomes a 2 by 1. So now we don't do any math with the numbers. It's just they get moved around. The rows become the columns. That's what a transpose of a matrix does. The trace of a square matrix is the sum of the elements of the main diagonal. So this only works for square matrices. Again, a trace is not a type of matrix. A trace is something that we do to a square matrix. Now, a square matrix is a type of matrix. So if I have a square matrix, I can take everything in the main diagonal, add it up, and that would be the value of my trace. Here's a matrix A, and you'll note that it's a square matrix, right? It's a 2 by 2 matrix. That means the same number of rows and same number of columns. This makes it a square matrix. This is the main diagonal. If I were to add the main diagonal, I would get the trace of A. In other words, 3 plus negative 1, and that would give me a value of 2. So the trace of this square matrix A is 2. Here is matrix F. This is also a square matrix. It's a 3 by 3 matrix. Same number of rows, same number of columns. Again, we look at the main diagonal, and we only do this for square matrices. The trace of F would be 3 plus 0 plus a negative 8. And so the trace of F is going to be a negative 5. I'm going to leave problem 5 up to you to give 3 examples for each of the above definitions.
Perfect. You win.
For your summary, give an example of a matrix that satisfies all of the following requirements at the same time. So it must comply with all 4 of these things: a square matrix, a zero matrix, a square zero matrix that has a trace of 0, and on top of that, it must be a row matrix. So don't make me 4 different matrices. Make me one matrix that satisfies all 4 conditions.